Unit 2, Activity 2, Exponential Functions as Models for Percent Change. Previously, we used exponential functions to model situations in which a quantity was changing by a constant factor, such as being doubled or tripled or being cut in half. In this activity, you will extend this idea in order to use exponential functions to model situations in which a quantity changes by a constant percent, which is another way of describing change by a constant factor. Learning outcomes, you will carefully document your work, including defining variables, and you will explain the meaning of constants in equations. You will explain why equations most model given situations and why results make sense. You will also make tables and write equations to model situations. You will use tables and equations to solve problems involving quantities that change by a constant percent, and you will demonstrate your ability to find percents and write equations to model data. And let's start with some warm-up problems. So here we will calculate each percent and then describe the result as a percent of the original amount. So check that your percent gives the same result. The first problem is done for you as an example. So let's discuss the first problem. Decrease 200 by 10%. So what you do is 200 minus 10% of 200. So how do we get to 10% of 200? 10% is equivalent to 10 over 100, or that's equivalent to 0.10. So 0.10 of 200 is 20. So 200 minus 20 is 180. So think about this. If 10% is taken away, then 90% remains. So if you subtract 10% from 100, then that is 90%. So we can say also that decrease 200 by 10%, meaning that's the same as 90% of 200. Do you agree? So look at this. If we get 90% of 200, that's 90 over 100, or 0.90 times 200 is also equal to 180. So again, decrease 200 by 10% is the same as 90% of 200. Okay, so let's do the same thing with the next example here. Decrease 80 by 72%. So just like what we did here, so 80 minus 72%, that is 0.72 times 80. And what is 0.72 of 80? That is 57.6. And 80 minus 57.6 is equal to 22.4. So decrease 80 by 72% is the same as, what do you think? So earlier, decrease 200 by 10% is the same thing as 90% of 200. So we got 90%, that's subtracting 10 from 100. So when we subtract 72% from 100%, so meaning 100 minus 72, that is 28%. Okay, so let's try that. What is 28% of 80? So 0.28 times 80, when you multiply that, is also equal to 22.4. So they are the same. Okay, so take note, decrease 80 by 72% is the same thing as 28% of 80. Next one, number 3. Increase 480 by 35%. So here we would increase our number 480 by 35%. From 1 and 2 we decrease, so we subtract. So if we increase, we add. So 480 plus 35% is 0.35 of 480. So what is 0.35 of 480? That is 168. And 480 plus 168 is equal to 648. Increased by 35%. Increase 480 by 35% is the same thing as, so we increase, so we add that to 100%. So for decrease, we subtract it to 100%. So here increase, so 100 times plus 35% is 135% of 480. So let's check that. 135% of 180 is the same thing as 1.35 times 480, and that is equal to 648. So they are the same. Okay, so don't forget here, increase 480 by 35% is the same thing as 135% of 480. So let's do the same thing for number 4. Increase 24 by 6.5%. So increase 24, so 24 plus 6.5%, that's 0.065 of 24. And what is 0.065 times 24? That is 1.56. And if we add that by 24, the answer is 25.56. And like what we did earlier, increase 24 by 6.5% is the same as the word increase. So 6.5%, we add 100%. So that is 106.5% of 24. And if we try that, if we move the decimal 2 places to the left, so that is 1.065 times 24. 1.065 times 24 is also equal to 25.56. Okay, so again, don't forget, increase 24 by 6.5% is the same thing as 106.5% of 24. Okay. All right, now let's start with our class discussion for this Unit 2, Activity 2. The first problem: at community colleges, students may enroll in one class, several, or enough to make a full-time schedule. Because of the differences in the number of units students take, colleges calculate FTES, or what we call it as full-time equivalent students. So for the California community colleges, the number of FTES a college has determines how much funding the college receives from the state. The state universities and community colleges calculate FTES differently, but in both cases, FTES is a variable that estimates how many students would be attending the college or university if everyone is enrolled full-time. In 2005 to 2006, one community college had 4,000 FTES, and the college was prepared to increase the number of FTES 5% per year for the next few years. So we're going now to make a table to show the number of FTES for a 4-year period of time, from 0 up to the 4th year. So X is the the number of years since the 2005-2006 academic year, and y is our projected FTES at the college. So at the beginning, 2005-2006, the community college had 4,000 FTES. So you should have 4,000 here. So now after the first year, it increased the number by 5%. So remember from our warm-up, it increased by 5% is the same thing as, very good, 1.05% of 4,000. So now what is 1.05% of 4,000? So that is going to be 4,200. So increase by 5% every year. So next now is increase by 5%. So that is 1.05 of 4,200. So that is 4,410. Then next, we do the same thing, increase by 5% on the third year. 1.05 times 4,410 is 463.5. Since we're talking about enrollment here, so let's say 301 approximately, and then increased by 1.05% again. With that, you will have here 4,862. Okay, so that is a 4-year period of time. Okay, so write an equation of the function and use the function to project the FTES 10 years later. So what's going on here? So remember our exponential. It's going to be y is equal to a times b raised to x. To recall, our general form of an exponential equation is y equals a times b raised to x, where a is the initial value and b is the growth or decay factor. So we talked about that last activity 1. So write an equation for the function and use the function to project the FTES 10 years later. So this one, y equals initial enrollment at the beginning of 2005. We have 4,000, and every year, as you can see here, it says that it's increasing by 5% every year. Increase by 5%, so that's 1.05 raised to x. So this is our equation. And then project FTES 10 years later. So all we have to do is solve f of 10. So that is 4,000 times 1.05 raised to 10. And that is going to be approximately equal to 6,515.6. So that is 6,516. So after 10 years, it's 6,516. Okay. Letter C, the annual increase is 5%, and so 10 years later, you might think the FTES are 50% higher than where they started, or 5% per year times 10 years. Why is this incorrect? So we computed increasing by 5% every year. F of 10 is 6,516 compared to what is, if you think about 50% higher than the original when it was back in 2005, which is 4,000. So let's try 4,000 plus what is 50% of 4,000, which is equal to 2,000, and 4,000 plus 2,000 is 6,000. And it's not the same as 6,516. So that's why it is incorrect. Number 2. In the current economic times, community colleges have to decrease the number of FTEs. LMC had about 8,000 last year. What if we had to decrease our FTEs by 6% per year? So decrease by 6% per year. So remember from our skills practice warm-up, when we decrease, we subtract this from, yes, 100%. So it's like 1 minus 0.06 is equal to, that is 0.94. So let's complete the table and write an equation for this. X is the number of years from when the decrease in FTEs began, with the number of FTEs, which is 8,000 at the beginning. Y equals f of x, that is the projected FTEs. So here, if we decrease by 6%, so at the beginning it was 8,000. After a year, a decrease of 6%. So that is the same thing as 94% of 8,000. So that is 0.94 times 8,000. Which is equal to 7,520. Next, decrease again by 6%. So, or that's the same thing as 94% of 7,520. That is 7,000, approximately 7,069. And then decrease again, and for the third year, decrease by 6%, or that is 94% of 7,068.8, which is equal to 664, approximately 6645. And the last one, do the same thing. 0.94 times this is going to be 6246. And then now we're going to write the equation of that function. So y is equal to, we started, remember again, just to recall, y equals a times b raised to x. This is the general form of the exponential equation. So at the beginning, the initial enrollment was 8,000. And then our b, since there is a decrease of 6% per year, that's the same thing as 94%. So that is 0.94 raised to x. So this is our equation. Now let's use a calculator to estimate the FTEs. That would be down to only 5,000. So use a calculator. Let's use Desmos. These are Desmos. All we have to do is just type our equation here. Y equals 8,000 times 0.94 raised to x. And we can change our values here. Let's say 8,000. Say -10. So this is the graph of that exponential. It's decreasing by 6%. And to get the table, let's change this to the table of values, and let's project what's going to be when it's going to be 5,000. So if it's on the third year, on the fourth year, on the fifth year, it's 5,871. On the sixth year, it's getting close. About the seventh year, so I guess it's 7th, and then 8 is 4,876. So 5,000 is between the 7th and the 8th year. You see that? So again, using our Desmos, it's between the 7th and the 8th year. It's going to be 5,000. Okay, so don't forget, always go to your Desmos. That's the easiest way to graph. You just have to enter the equation 8,000 times 0.94 raised to x, and then convert it to table, and you can see this table of values. All right, number 3. Consider the functions h of x equals 28 times 1.27x and g of x 28 times 0.93x. Which one models growth and which function models decreasing quantity or a decay situation, and how do you know? So we did this back in activity 1, if you remember. Again, in the form of y is equal to a times b raised to x. The b part is where we know about the growth or decay. So b is the growth or the decay factor. I can write it down here. So when do we know that? We actually discussed this last time. That is when b is greater than 1, then there is a growth. When b is between 0 and 1, then that is a decay. Okay, so don't forget that. So you always think about your b. So the function here, h of x models growth, and g of x models a decay situation. Okay. Next, number 4. Find an exponential function for the data in the table. So given x from 0, 1, 2, 3, 4, and 5, r of x 500, 300, 180, 108, 64.8, and 38.8, it's decreasing. And we know again our general form of an exponential equation is in the form of y is equal to a times b raised to x. Okay, whereas a is the y-intercept of the function, that is also the initial value. So the initial value here is when x is 0. So we could say that y is equal to 500 times b raised to x. Now our question is, what is b? All we have to do is, to solve for b, we can plug in, let's say this is your x and this is your y to our equation. Let's do that. So y is 300 is equal to 500 times b raised to your x is 1. Now we can solve for b. So we divide both sides by 500 and now we can say that b is equal to 3/5. So now we can write our equation. So find the exponential function. So that's going to be y is equal to, our a is 500 and your b is 3/5 raised to x. So this is our answer. Okay, letter B. When the growth factor is a decimal, we explain change as percent. What is the percent change per 1x value in the table above? So our factor here is 3/5 and 3/5 is the same thing as 0.6. So we can change this to a percent. 0.6 or 0.60 is equivalent to 60%. So that answers our question, what's the percent change in the table above? So that is 60%. So we can change, try that. Look at this. 500, 60% of 500 is 300. 60% of 300 is 180, and so on and so forth. So the answer is 60%. Okay, and the last problem. Consider the equation y equals 5 raised to 2x. This function models a quantity that is doubling. Even though the growth factor is a whole number, which is 2, we can still describe the growth as a percent change. What is the percent change per 1x value? So that doubles, your guess is right, that is 200%. Okay? Alright, that's the end of activity 2, but you can see some group problems here. Maybe let's do this. Match each situation with the equation that models it. For each problem, define the variables. Let's match each situation with the equation here, and I'll let you work on defining the variables, okay? Letter A, Beth is hired with a starting salary of $30,000 and she is promised a 4% cost of living increase each year. So to write an equation here, this is going to be 30,000. Maybe they use 30,000 times increase, so that's going to be 1.04 raised to x. So this one. Letter B, an initial dose of 30 milligrams of zinc is metabolized by the body so that each hour is 4% less zinc in the blood stream. So 4% less, we subtract that from 100 and that is 0.96 raised to x. So this one. Letter C, the cost of a quart of milk is 1.04 in 1990. So that was the initial value. So y is equal to 1.04. The prices rise as a result of inflation, which is projected to be 34% each decade. So that is increase of 1.34 raised to x. And letter D, the cost of computer was $3,000 in 1995. One analyst predicted that technological advances would cause the price of comparable computers to decrease by 3.4%. So if you subtract this from 1 minus 0.034 is equal to 0.966. So y is equal to 3,000 times 0.96 raised to x. So this one. Okay. So like what I said also, for letter A, that 30,000. Since the choices is 30, or if you really want to be specific, this is going to be 30,000. Okay, and like also please don't forget to define your variables. Okay, so that's it for activity 2. Let me know if you have any questions. Thank you.